Welcome back to recordings or video lectures in Calculus 3. Today's topic is going to be vectors and some equations in 3 dimensions. So I'm going to share the partial notes and let's get started. Any minute now. There we go. Alrighty, so we're going to start with a framework, specifically a 3-dimensional Cartesian coordinate system. And the question is, how do we set up axes for this system? Well, I know you can see the picture right there, but besides that, how do we do it? Alrighty, so we're going to use the right-hand rule. So here's the idea. The x-axis comes out of the page, as you can see. The y-axis is going to be horizontal, and the z-axis is going to be vertical. So what do I mean by the right-hand rule? If I let the x-axis be my fingers and the y-axis be my hand, you see my thumb is pointing in the direction of the positive z-axis. And the arrows in the graph here denote the positive direction. So we see that a point in 3-dimensional space, which is denoted by R3, requires 3 coordinates. And so it's written as the tuple x, y, z. Each pair of axes forms a coordinate plane. So the xz plane, if you're looking at the picture, would be when y is equal to 0. The yz plane would be when x is equal to 0, and the xy plane would be when z is equal to 0. And we can also see that in the textbook picture, which is right there. In 2 dimensions, right, we know the coordinate axes are going to partition the R2, the plane, into 4 coordinates. However, in R3, we can see that these coordinate axes are going to divide space into 8 regions, and these regions are called octants. We're not going to super worry about that, except in terms of thinking, where are my points on my object going to be? We can also define the distance between points in space in a similar way as for points in the plane. So how do we do that? Well, d is just going to be the square root of x2 minus x1 quantity squared plus y2 minus y1 quantity squared plus z2 minus z1 quantity squared. So as an example, let's just find the distance between the points 2, -3, 1 and 1, 2, 3. So just applying the formula, we get the square root of 3 minus 1 quantity squared plus 2 minus a -3 quantity squared plus 1 minus 2 quantity squared, which gives us the square root of 30. Again, if we're being good, we'll write that as, let me try that again. That's just the square root of 30. We can't be good and reduce that any. I just had a momentary brain where I forgot my multiplication tables. Okay, so let's look at writing some equations in R3. We're going to start by looking at some simpler geometric curves in R3. First, we'll talk about some simple planes. The simplest ones are going to be those that are parallel to the coordinate axes. As I mentioned before, right, the xy plane is when z is equal to 0, so the points on the xy plane have the form x, y, 0. And then the equation for the xy plane would thus be z is equal to 0. Similarly, the xz plane is given by the equation y equals 0. So what is the equation for the yz plane? You should think a moment, pause the video before I answer the question. Okay, so what is the answer? If you came up with x is equal to 0, then you are absolutely correct. That is literally the answer. Okay, in general, the equation of a plane that's parallel to one of the coordinate planes can be written as follows. So let's just suppose that our plane is going to contain the point ABC. If we want it to be parallel to the XY plane, that means Z is going to have to be constant, and so Z is equal to C. If we want the plane to be parallel to the XZ plane, that means Y is going to have to be constant, and so we obtain Y is equal to B. And finally, if the plane is going to be parallel to the YZ plane, we need X to be constant, and so the equation would be X is equal to A. Let's look at examples with real numbers now. So let's write the equation of the plane passing through the point 1, 2, -4, and parallel to the XZ plane. So parallel to the XZ plane means Y must be constant, so we need Y constant, and since the Y in our point is 2, that's going to give us the equation Y is equal to 2. No, all examples in this course are not going to be this short, but it's nice to start off gently. Next thing, let's do one more example. On this, let's find the equation of the plane passing through the points 1, 0, -2, 0, 8, -2, and -3, 4, -2. So if we look at those 3 points, the X components are all different. The Y components are also all different, but the Z component, the Z coordinate, is identical in all 3 points. So the Z coordinate is identical or the same in all 3 points, which means that the equation must be, what do you think? If you're thinking and you said Z is equal to -2, then you are absolutely correct. Okay, another sort of simpler three-dimensional object is a sphere. So kind of like a circle, right? A sphere is defined as the set of all points in space that are equidistant from a given fixed point, which is called the center of the sphere. And the distance from the center of the sphere to a point on the sphere is called the radius of the sphere. So the equation of a sphere of radius r centered at the point ABC is given by x minus a quantity squared plus y minus b quantity squared plus z minus c quantity squared is equal to r squared. Awesome. All right, so let's do a quick and handy dandy example on this, if you don't mind. Well, actually, even if you do mind, right? Because I'm the one recording the video. Okay, let's find the equation of the sphere with diameter PQ, where P is the point 1, -1, 2, and Q is the point 3, 1, 4. So we have to do 2 things here. We have to find the center and we have to find the radius. So the center is going to be the midpoint of PQ. We'll call our center ABC, and that's the midpoint of, again, our diameter PQ. And we know how to find a midpoint from algebra, right? So we just take the average of each coordinate. So 1 plus 3 divided by 2 is the x coordinate. 1 plus -1 divided by 2, is the other coordinate. And the final coordinate is 2 plus 4 divided by 2. So we get that it's centered at 2, 0, 3. The radius is half the length of the diameter, so it's half the distance from P to Q. So we use the distance formula that we talked about just a few moments ago. So we get what you see me writing here. Okay, so if you do all the work, you get that that's 1/2 times square root of 8, which is just square root of 2. So r squared, which is what we need for the formula, right, is going to be square root of 2 squared, also known as 2. And our equation of the sphere is going to be as follows. So I'm going to have x minus 2 quantity squared plus y minus 0 quantity squared plus z minus 3 quantity squared is 2, or writing that just a little more nicely, because y minus 0 is just a y, we get this equation here. Awesome, so that's our equation of the sphere. And we didn't have to break a sweat. Well, I guess if you're outside and it's hot, you might be breaking a sweat, but in terms of doing the problem. So one other equation in in R3, one other equation in R3 we're going to talk about is, well, I'm going to do this one by example. So suppose I have the equation x minus 2 quantity squared plus y minus 3 quantity squared is equal to 4. We know that's a circle if we're in the xy plane, but what is it in R3? Well, shucks. Okay, so again, in the R2, in the plane, we see it's a circle of radius 2, centered at 2, 3. In R3, we see that there's no z appearing in the equation, which means z can be anything. And so what's going to happen is we're just going to have a bunch of circles. In fact, we're going to have infinitely many, which gives us a cylinder, and that cylinder is going to extend infinitely in the plus and minus z direction. And the horizontal cross sections, again, are going to be circles centered at the vertical line that goes through x equals 2 and y equals 3. So this is roughly a picture of said cylinder. Well, it's obviously a snapshot because it's infinitely large, so we can't really see all of it. All right, how about another fun example brought to you by Good Times Rolling? Here we go. What is the graph of x minus 2 times z plus 1 equals 0? So first of all, from algebra, we know that this is true if what? Well, there's only two possibilities. That is that x is equal to 2 or z is equal to -1. And so basically what that tells us is that the graph is the two planes, x equals 2 and z is equal to -1. So this was a fun introduction to graphs in 3 dimensions. Okay. Now let's talk about vectors in R3. So vectors in R3, 3 components. So the component form, again, don't forget those angle brackets, x, y, z. So the 0 vector is 0, 0, 0, surrounded by those angle brackets. Vector operations, component-wise, defined exactly the same way as for vectors in the plane. Graphically, we denote them as a directed line segment in R3, right, in x, y, z, from the initial point to the terminal point, where those are defined the same. And we play with vectors in R3 the same way. We can extend the standard unit vectors to 3 dimensions and add 1 for the z. So I is going to be the vector 1, 0, 0. J is going to be the vector 0, 1, 0. And K is going to be the vector 0, 0, 1. So any vector V, being x, y, z, right? So with our angle brackets, can be represented using unit vectors as x times I plus y times j plus z times k. And the operations with vectors in 3 space, in 3 dimensions, I reproduce them below, but you're going to notice that they're pretty much the same, right? We have scalar multiplication, we have vector addition, we have subtraction. We can find the magnitude, right? Remember, magnitude is basically if we have the point whose the vector and put its initial point at 0, 0, and its terminal point at XYZ, right? It's just the length of that, the distance between the 2 points. And to normalize, we divide our vector v, if it's not 0, of course, by the magnitude of it. And all of the properties for vector addition and scalar multiplication that we already talked about are satisfied by vectors in R3. So I think we will conclude this video with one short example. Let's let A be the vector 2, -1, 3, and B be the vector -1, 3, -4. Let's find 2 times A minus 4 times B and write the result using standard unit vectors. So we're going to write the answer 2 ways. So first, 2 times A minus 4 times B is going to be 2 times 2, -1, 3, minus 4 times -1, 3, -4, which is going to be 4, -2, 6, that vector, minus the vector -4, 12, -16. So that's going to give me 4 minus a -4, -2 minus 12, and 6 minus a -16, also known as the vector 8, -14, +22. And writing that in standard unit vectors, using the standard unit vectors, I should say, we get 8i minus 14j plus 22k. And like always, there are some suggested exercises for additional practice for you. I hope that this video was helpful, and I want you to have a great day, and I will see you soon.